Hi, I'm Lisa Taylor, President and CEO of the National WASP Museum in Sweetwater, Texas. With me today is Dave. He is our BT-13 pilot, and he's going to be giving you a tour of this beautiful BT-13 aircraft.
All right, let's go to the cockpit. So we're here in the cockpit of the Vultee BT-13 at the National WASP World War II Museum. This is a 1942 model BT-13, just like the ones that the ladies would have trained in here at Avenger Field in Sweetwater, Texas, as part of their basic training. They went through primary, then basic, and then advanced training. The BT-13 was the basic trainer that everybody in America used during World War II. So I just wanted to show you around the cockpit a little bit. The primary flight instruments are very conventional. A stick in the center to control pitch and roll, just like every conventional airplane, and rudder pedals to control yaw. The pedals you move with your feet also incorporate the brakes on the ground. You press the tops of the pedals, and you can press either brake or both brakes at the same time to either stop straight ahead, or to turn to the right, or to turn to the left. That's how you steer the airplane on the ground. Second, we'll talk about the secondary flight controls, which are all here on the left side of the cockpit. They're secondary because they're not what you're moving every moment. They're trim controls to set the airplane in the flight conditions that you need at the time during your flight. So these two wheels here on the left are the trim wheels. The first one controls pitch, nose down. You roll it forward to go down. You roll it backward to go nose up. That's very intuitive, very easy to understand. The outside one is the rudder trim. Forward is nose to the right, and backwards is nose to the left. That's a little less intuitive, but less frequently used trim control also, and very easy to get used to over a little bit of time. Next, secondary flight controls is the flaps. They change the shape of the wing for better slow flight characteristics. Nothing in this airplane is automated or power assisted. It's all a mechanical device, including raising and lowering the flaps. So you raise the flaps by cranking this handle forward. You get 2 degrees of movement for every complete turn of the crank. When you're flying the airplane, your head's up, looking out the window, looking out the canopy, looking at these instruments in front of you part of the time. You don't look down here, you count turns, and you just learn that I need 10 turns to get 20 degrees of flaps. Most pilots will use 20 degrees of flaps for takeoff, 40 degrees of landing. There are up to 60 degrees of flaps available in this airplane, which most pilots will tell you is a lot of flaps. You can really come down in a hurry. Gives you a lot of control over your rate of descent using the airplane. Going on from flight controls, let's talk about engine controls. Again, here on the left side of the cockpit are the primary engine controls. You can tell that the designer intended the pilot to fly the airplane all the time with his right hand and use his left hand for all of these controls around the cockpit, even reaching over to the right to control the radios. So the engine controls will start at the bottom. Black knob is the propeller control. This airplane has a two-position propeller. Forward for high RPM, low pitch. You use that position for takeoff and climb, or back for high pitch, low RPM. You use that for cruise, more efficient cruise conditions. Red knob is the mixture control for the engine. Those of you that are familiar with internal combustion engines will be familiar with carburetors. An airplane operates in many different pressure conditions, from all the way down at sea level to high altitude. The ideal engine mixture of fuel and air, is different at all those different conditions. The pilot has to have a control available to set the ideal mixture at each flight condition. The knob that sticks out the farthest here is the big knob. It's the throttle control that controls your engine power. Forward for more power, back for less power. analogous to the foot feet on your automobile. Other engine controls that we have would be kind of secondary engine controls for special conditions. We have here on the bottom an oil cooler shutter. This engine is air and oil cooled, so we have a gauge on our instrument panel that tells us oil temperature at all times, and you can control the amount of air flowing to the oil cooler to control your oil temperature. Up here is carburetor heat. Old-fashioned carburetors, especially in airplanes, have the potential to generate ice by condensing water out of the air as it flows through the carburetor, and that can choke down the engine and cause it to stop. So we have a control here that lets us direct engine exhaust heat into the carburetor to melt any ice that's building up. Finally, we've got a fuel control valve here. This airplane has 2 fuel tanks, one in each wing, 60 gallons in each, and you can select with this handle left tank or right tank or a reserve position, which is actually just the last 17 gallons in the right-hand tank. Typically, the airplane burns about 20 gallons of fuel an hour. Each tank holds 60 gallons for a total of 120. So a typical maximum flight plan would be 5 hours of flight with an hour of fuel reserve. Most of us are even more conservative than that. Besides, 5 hours is a long time to sit in this seat. A lot of times we plan for 3 to 4 hours for a cross-country flight before we stop and refuel. That covers everything on the left-hand side of the cockpit except for this big red handle here. And passengers are always interested in that because it's red and big and noticeable. That's actually your mechanical fuel pump. The engine wings, of course, are low wing in this airplane, so to get fuel from the tanks into the carburetor, you need a fuel pump. The engine drives a mechanical fuel pump when it's running, but until it's running, you have to have a way to fill up the carburetor so you can start it, and that's what this pump does. The pilot just pumps up fuel pressure with a hand pump fuel where it needs to be until the engine starts running. And once it starts, it will pump its own fuel and pull fuel and air through the carburetor and keep running. Let's talk then about the instrument panel. Most interesting parts of the instrument panel, we'll start on the left. We have an ignition switch that controls the engine ignition. So when it's off, the engine cannot run, no spark to the cylinders. We have dual magnetos. Normally we run on the both position, so they're backing each other up and the engine will keep running even if there's a partial failure. Across the top of the instrument panel is the primary flight control instruments, flight and navigation. We have altimeter, an airspeed indicator, a turn and bank indicator that the pilot can use as a navigational instrument as he flying straight and level, is he coordinated, a vertical speed indicator, and then a vacuum suction gauge which reports how well the power is performing that powers your gyroscopic instruments. Above here we have the gyroscopic instruments, a gyro compass that is adjustable and used for navigation, and a whiskey compass, a traditional magnetic compass that works if everything else on the airplane quits, the magnetic compass will still work, and an artificial horizon. These two instruments are driven by gyroscopes, and they need power to run those gyroscopes. This gauge tells you that you're getting good power so that you can believe the readings that you're getting from your gyroscopic instruments. And we have a clock, because I mentioned fuel and time. Fuel time calculations are very important in an old-fashioned airplane, so you don't run out of fuel unexpectedly. So next, let's talk about the engine instruments. This row here are engine instruments. Primary importance is the RPM, how fast the engine is running. This is our engine condition gauges. It's 3 gauges all into one. We've got oil temperature here, and you can see we have the green zone, the good zone marked, so the pilot can just look and see if his needle's in the green. He doesn't have to read the number. Everything else is fine. This part of the gauge here is fuel pressure. It has a green zone. And this is oil pressure, and it has a green zone. And here we have cylinder head temperature. For an air-cooled engine, you have to be sure that you don't overtax the engine to get it so hot that the metal begins to break down in the pistons. So you keep your engine temperature within this green gauge, you're good to go. If you get too hot, then you need to ease back your power consumption and change your plan. Next in the row, we come to avionics. This little control head here is our communications, our VHF radio control head. This is our transponder for air traffic control. These are modern avionics that are required to fly the airplane today in modern American airspace. I wanted to point out to you these boxes here on the right-hand side of the cockpit. We talked earlier about how the airplane was flown with your right hand and all the controls are on your left. On the right side of the cockpit here are the avionics, the radios that the airplane had in 1943. These two boxes, transmitter and receiver, would be HF frequency, high frequency band communications radio equipment in that time period. There's a big antenna on the outside of the airplane. These are not operational today. Modern avionics is based on very high frequency and 1 gigahertz band radar transponders. Those are required in every airplane to fly in modern American airspace. So we've taken the insides out of these boxes. They appear realistic. Inside there are modern solid state electronics for VHF radio and the transponder. And here on the instrument panel we have control heads hidden away, trying to blend in with the 1940s instruments and the 1940s motif of our cockpit. I think they do a pretty good job of hiding. Finally, in the cockpit, we look at the electronic control panel here. Electrical control panel across the bottom. We have switches for lights, the engine starter. We have cockpit lighting. We have spotlights of various kinds, lighting for landing lights and taxi lights. We have a voltmeter and an amp meter to tell us the condition of our charging system. The engine does have a generator, not an alternator, for those of you that remember the difference in what things were like back in the bad old days in the 20th century of generators. And over on the far right here, we have the circuit breakers for all of the systems included in the airplane and an avionics on-off switch. Right in the middle, cockpit temperature controls, hot and cold, parking brake, and an alternate air valve in case there should be any damage to the pitot tube in the airplane. You can open alternate air and still get instruments to operate long enough for you to land the airplane safely. Thank you.
Live and cut.
So let's talk for just a second about the numbers that are on the side of the airplane. Here on the tail, we have the serial number of the airplane. And every airplane has a different serial number. There's a little bit of information here. The 2, the first digit of the serial number, tells us what year it was built. So this is a 1942 airplane. And then the other digits are just the sequence that it was built in. Army used put these numbers on the tail so they could keep track of inventory. Walk down the flight line, count which airplanes are there. Here on the side of the fuselage, we have the ship's number. These have a lot of different names that people use, mostly slang names. I typically call it a buzz number. And the reason that is each airfield painted their airplanes with these large numbers on the side of the airplane so they could identify the airplane from the air. And so that civilians living around the airbase could report pilots who were misbehaving and buzzing the town. That's why it's called a buzz number. We put number 55 on this airplane to honor specifically the class of 1943 W7, the Women's Air Force Service pilots that trained here in Sweetwater at Avenger Field. Airplane number 55 looked exactly like this, was in their yearbook. And there's a photograph there of 6 of the WASP from that class standing with this airplane, smiling and proud of their accomplishments in passing basic training. So people have noticed the compass correction card in this aircraft, and realistically that's in every aircraft. Passengers just can't usually see it. And what that is for is this is a very simple magnetic compass, just like used in Girl Scout cross-country training and so on. And being located, mounted here in the airplane with all of this metal around it, some of it steel, some of it aluminum, big iron motor in the front, although that metal makes subtle influence on the magnetic field that this compass experiences. So for every airplane installation, a mechanic goes and parks the airplane on a compass rose that's been laid out by a surveyor to be perfectly aligned with magnetic north and south and east and west, and moves the airplane on that compass rose and reads off what heading the compass actually indicates when it is pointed perfectly north. And then there are notes made for the pilot here. In this case, I can see that if I want to steer perfectly north, 360 degrees, I have to make the compass actually say 003 degrees, 3 degrees to the right of perfectly north. Directly east, 90 degrees is 90 degrees, and it reads perfectly in that case. Directly south is perfect, 180, 180, perfectly correct for west, 270, 270. Those numbers are different for every airplane. They'll be different for every BT-13. Typically they're within 2 or 3 degrees of the perfectly correct number. But this actually is a really good installation that 3 of them are perfect and only 1 of them is off by 3 degrees.